Theoretical particle. I'll start again. Ankita is a theoretical particle physicist working in quantum chromodynamics and jet physics, with a focus on effective field theory methods for precision studies of jet observables in both vacuum and thermal media. So she obtained her PhD from the Institute of Science, Education and Research in Bhopal, and subsequently held a postdoctoral position at Tata Institute of Fundamental Research in Mumbai. She currently holds a postdoctoral fellow at Nikhef, leading particle physics institute in the Netherlands. So her current research focuses on a specific class of jet observables called energy correlators that have raised a lot of attention in the community recently. Through her talk, Ankita will convey the importance of the observables in improving our understanding of the strong interactions and the specific research contributions in this direction that she has done. So you can take it away, Ankita.
Thank you. Thanks a lot. Thanks for the nice introduction and also for the invitation to give this seminar. And by the way, I should mention I was really happy with the post, the way you advertise things. I was very happy to have a poster style thing with my face on it. So I downloaded that. This is the first time I get this thing, which is nice. So I don't know like what's the culture here about questions, but since it's an online seminar, I would really appreciate if the questions are during the talk so that I can also feel more connected, really. Okay, so with that, I want to talk about the topic which is said here, probing jet dynamics with higher point energy correlators. And if you know nothing about this, then it seems like a lot of words. So what I would try to do right now is to try to like dissect this whole title piece by piece. So to start with, let's talk about what these energy correlators are. What's the general idea behind it? So in our particle collision experiments, we collide particles like electrons, protons, or even larger nuclei, and out comes a bunch of like lots of particles that deposit their energies and momenta in the detector elements that we construct. And from this energy depositions that we have in our detectors, we would like to really trace back the history of these particles and try to understand the fundamental interactions of the elementary particles that resulted in this energy flow that we observe in our detectors. Now, the situation is actually really similar to what we also do at larger scales at the universe. For example, in looking at the CMB temperature maps, where we see the CMB temperature map of the universe, and by looking at the fluctuations at different space-time points in this map, we try to understand how the structure formation happened in our early universe. So just to go a bit further about what correlation functions are, as I said, by looking at how the temperature fluctuations emerged in the CMP temperature map, what we try to do is to get something which shows how the different fluctuations emerged in our universe. And same way in particle collisions, the fundamental correlations that we observe are the correlations of this energy flux, so how the energy flows in our collider elements. And from that, we want to trace down how the fundamental interactions look like to get something like the bottom plot that you see right now. And the most simple element that you can construct in order to study these correlations in energies is what is called as energy correlator. And all the energy correlators that I will talk about in this talk are going to be measured on what are called as jets. So first, I would like to get rid of this jargon. What is a jet? In very simple terms, a jet is basically a collimated spray of energetic particles that are all like following inside a cone of specific radius. Now, what is an energy correlator? So in simple terms, now you have a jet with a specific number of particles that are all moving in a same direction inside this jet. You take any two particles at a time, look at what is the separation between the two particles, bin your histogram in terms of this angular separation of the particles, and each histogram bin you weigh by the product of energies of these particles. So at every angular separation, you are looking at how the two particles are correlated in energy. And then the hope is that by looking at this correlations at different energy or angular scales, you will be able to see like different correlations emerging in between particles. So this is a general idea of the simplest two-point correlator that you can construct. But of course, you don't have to stop at constructing only correlation between two particles. You could go to higher number of particles inside the jet. For example, I cannot see my cursor. Can you see my cursor anywhere on the screen?
You cannot. No.
Okay, maybe it's better that I do this because I think Keynote removes that. Does this go better or should I go to the full screen only?
This looks good. This is fine.
Okay, okay. So for defining higher points, you can imagine that now you pick, for example, 3 points in your jet. And one of the simplest thing you could do is, of course, when you take more power points in your jet, you are looking at more resolved correlations in your jet. But one of the simplest things that you can do in the same spirit of just doing the two particle correlations is by integrating out the shape information of this full correlation and only keeping the like larger separation between the particles intact. This is what goes by the name of projected energy correlators, and this will be one of the most relevant observables for this talk that I'll come back to later. Okay. Yeah, so now I want to first also convince you like why these energy correlators are like so interesting or why they have created all this hype recently. So as a simple example, what you can learn from these observables, since as I said, like by looking at different, since you map out correlations at different angular scales, your hope is that once your scales are perturbative, you see uh, imprints of the perturbative dynamics in that. And as your scales become smaller and smaller, which is the place where you reach to the non-perturbative regime, you see some kind of transition happening. And fortunately, these class of observables are the first class of jet observables that have really allowed us to clearly visualize this process. So if you look at the plot below here, now the relevant scale here plotted on the x-axis is the angular separation, but in order to think about where perturbative or non-perturbative regime lives, the relevant scale you should think about is the pt times this scale. So if pt times this angular separation is large, your scales are perturbative. Once pt times this scale becomes of the order of 1 GeV or size of your proton, you expect non-perturbative dynamics to take over. And what you see really in this plot, this is showing that, okay, in the region where your RL is large or PT times RL is perturbative, you see that the predictions in the data are actually very, very well in agreement with our perturbative computations. And later at some point at a scale, which is when your non-perturbative dynamics hits over, you see a different power law behavior, a different scaling behavior. And what people found is that this scaling can also be explained very simply because at this point, what you have is just a gas of hadrons. So you can fit it very simply with just a free streaming gas of particles. So now this was first predicted or checked in CMS open data. And then very recently, this has also been measured in experiments and the same behavior has been found in experiments. So this is really neat.
Can I ask a question?
Yes, sure.
So I was wondering, you have these two regions, and in the center you say you have this region where the you get this confinement of your
Yes.
constituent particles. So is that region well understood, or is transition difficult to understand? And how is it treated?
That's actually the very good question, really, because at present, this is the least understood region. So you know where at some point that, okay, you can also compute realistically, right? Like you can say that the relevant scale, as I said, it's PT times R. If PT times R becomes of the order of, let's say, lambda QCD or 1 GeV something, you expect that around that region, you see a transition. But this region, exactly how it transitions is not well understood. you can understand very well this perturbative region. This region can be understood, the power law can be understood by a single like linear behavior because it's just a free streaming gas of particles. But this is the least understood regime right now.
Okay, thanks.
Yeah. Okay. And what is really also nice, if you look at the experimental results further, you see that in the below plot, I'm showing this for three different values of PT. And as I said, since angles is not the best parameter to show these plots with, the relevant energy scale is PT times R. So if you scale with that PT of the jet that you're observing, you see that this scaling behavior is actually universal, which is very, very nice. Okay. The other thing which recently these observables have been utilized for is for uh, precision determination of your strong coupling. And the idea behind that is basically you take the higher point correlators that I defined, the projected. So you take the, let's say, 3-point correlator and keep only the largest separation between the particles intact, integrating out other directions, and take its ratio with the 2-point correlator. By doing this, what is nice is this, that in the perturbative region, the scaling behavior is really governed by there is a classical term and there is a modification that comes purely from the presence of anomalous dimensions. So you really start seeing impacts of pure quantum anomalous dimension scaling in the slope of this ratio. And of course, the other nice feature is that a lot of sources of your systematic uncertainties coming from ill-understood regimes or your non-perturbative effects would cancel out in the ratio. So by taking this ratio, what you see, this is done for like actually three different colors, as similar to the previous plot. So you see two things. First, that the ratio at small angular scales is nearly flat, which is the non-perturbative region. And in the ratio in the perturbative region is actually like has some slope. It's changing when you take the ratio of 3-point to 2-point, which signifies the presence of your anomalous dimensions. And the other thing that you see is that the ratio also changes a bit depending on the PT, which is the running of the alpha S effect, right? And from that, the CMS collaboration extracted the value of alpha S from these ratio of this energy correlators, and they could achieve this incredible precision of 4%, where the dominant source of uncertainty really lives in the theoretical input, actually. Yeah, but this is the most precise extraction of alpha S from any of the jet substructure observables that we have constructed so far. So it's really nice. Okay. The other thing I would like to say would be that not only these two things because of which these observables are really nice, but recently people have imagined really new territories where these observables can be applied. One of them is, for example, the precise determination of the top quark mass. And here, basically, the idea is that because of the presence of like the intrinsic three-body like decay of the top quark, you can use some particular projection of a 3-point energy correlator that allows you to isolate the peak, which is reminiscent of the top quark decaying into the three particles. And the hope is that this whole endeavor would lead us to better controlled theoretical uncertainties on the extraction of the top quark mass. Not only top quark mass, but these observables have recently also been applied for understanding effects of medium-induced effects in heavy ion collisions. And again, the basic idea is simple. The basic idea is that depending on, if I study correlations at different angular scales, it's probing the QGP at different length scales. And by looking at the correlations over all angular scales, I should be able to see impacts of different physics origins in the presence of the medium. And recently, this has also been measured by the CMS collaboration, and I'll come back to this later again. Okay, so with that, I tried to tell you about like what are energy correlators and why they have gained so much relevance recently. Now, I want to tell you a bit more detail about like these higher point energy correlators, what they are and what their usefulness could be. So I already introduced briefly projected correlators, but I want to define it a bit more like from the perspective of effective field theory, the formal way of how you really write down these observables. So for the simple case of a simple two-point energy correlator, the nice thing is that if you look at the factorized structure of this observable, it exhibits only a simple collinear factorization. So you get a hard function that describes basically the production of the energetic particle that initiates the jet, and all the final angular measurement of the correlator is encoded inside this jet function. Now, you can generalize the idea to go to higher points where you will have more structure, more angles involved. And of course, it starts becoming more and more complicated because as you increase the number of particles that you start correlating, you'll have to consider all n minus 1 by 2 pairs of distances between them. But the simple generalization, which I defined earlier, could be obtained by instead only keeping the largest separation imposed by this delta function constraint and integrating out all the other shape information about this correlator. Now you can ask the question that since it's also keeping only the 2-point information, how is it different from the standard 2-point correlator? It differs from the standard 2-point correlator because of the energy weights, because all the other particles' energy weights are still involved. So you basically are looking at different moments of the splitting functions in that sense. And the nice feature is that for the projected endpoint correlator, that you again then get a similar factorization structure in terms of the jet function and the hard function, a simple pure collinear factorization structure, where now the jet function becomes n dependent on how many particles you were resolving in order to define your projected correlator. Okay.
Sorry,
Yeah.
a silly question. For when you're looking at higher point correlators here,
Yes.
some kind of problem of aliasing, where if you projected out all the separations apart from the largest one, could you not have some high point correlator look like a lower point correlator just with higher energy? Say a 4-point correlator looks like a 2-point just with much higher energy of those two particles.
Yes, intrinsically it is, because right now, as you said, exactly, right? Like since you are projecting out to a single distance, right? So you are actually like, I mean, I would not say it's energy way differently, but yeah, because um, the only place where the energy of the particles that you integrated out comes in terms of this the external momenta of the particles that you multiply with, which changes the evolution actually, like fundamentally when you finally look at how these particles evolve, because now n moments of these energy weights contribute really.
Okay.
So it just changes the evolution, but I want to talk about a bit like how this evolution would be actually interesting to study. But
Right.
you're right. Like you are fundamentally reducing all higher point correlators into a 2-point correlator. And it's nice because now you can actually talk about any arbitrary endpoint correlator by just talking about a single scale. Otherwise, when you go to higher and higher, you are always having more and more scales in the problem, which is already also interesting in some way. But this is also still a general feature that you can do, and it already gives you quite a lot of features which are interesting to study, and that's what I want to come to.
Okay.
So just one follow-up question.
Yes.
So you're integrating integrating out certain like the higher contributions to your endpoint correlator to get effectively a lower point correlator to reduce the number of variables that you have in your solutions. Is that sort of what the idea is? Why you want to like go to a lower point correlator and integrate out the higher
I
Solutions?
Okay, so philosophically, it actually started with the thing, I don't know, like, so there is a different kind of observable, which is called as, it's also a jet observable, it's called as angularities, and it was at some point really famous in the past. And one of the reasons why it was famous in the past was because this particular observable has a free parameter. If you tune this free parameter, you actually allow yourself to change how you are giving the weightage to collinear versus soft radiations in your jet. And people liked it because you can actually understand how the different weightage of this collinear versus soft radiations impacts the final distribution of your observable in a continuous way, rather than just every single time measuring a single observable on the jet. So when this projected correlators were introduced, the idea was actually something similar, that you want to have a class of observables where you have somehow like a same angular scale, or same, your left hand side depends on the same variable, but you're still able to talk about like some information about the higher points, right?
Right.
So the way that information of the higher points goes is in the different number of powers of this energy fractions that were involved in your, but you have reduced down the problem to actually like just a single variable, if you like.
Okay,
Right.
thanks.
And there is no reason that you do not want to do like the full resolve thing. Of course, people do the full resolve thing as well. But I'm just saying that, okay, this already, like this reduction already gives you some very nice features that I want to talk next about. And basically, this is what my entire talk will be. These are the observables I'll focus on. Yeah. Okay. So let's move on further. Okay, one of the nice features that I have been saying about. So if you take the ratios of these projected correlators that you defined for different n values, and let's say here the ratio is defined with the simple 2-point correlator, which does not have any further structure to it, then what you find is that the power law scaling in the perturbative region is entirely governed by the anomalous dimensions. And you can see that the anomalous dimensions actually look like basically different n moments of the splitting function. So when you're looking at different n values, what you're really looking at is basically some specific moment of your splitting function. And what you see in the ratios is basically this, that in the perturbative region, since the only modification is because of this anomalous scaling, you see this impact of this anomalous scaling in the ratio by looking at by visible in the slope of these ratios. And in the non-perturbative region, you see like, okay, there are differences, but it's basically flat, right? So it's just some constant difference basically. So that indicates to you that, okay, in these ratios, the dominant effect of this non-perturbative distributions actually effects more or less cancel out apart from some constant factor, which is why it allowed this CMS collaboration to have such a nice prediction for the alpha S from the ratio of 3-point to 2-point correlator. Now, mathematically, nothing prevents you to keep taking just only like n to be an integer. It's for us, of course, it's easier to think about n being integer because you're literally thinking about like correlating some specific number of points. But as I said, like mathematically, nothing prevents you to take n to be non-integer. You can think about n being a non-integer by analytic continuation. And if you do think that way, then what's interesting is that if you take n goes to zero limit, you see what you are weighing more strongly changes, because now you are weighing more strongly particles with small momentum fraction. So you gain access to small x physics using jets, which is a very novel application that you can do. Okay, so now how do you really define this analytic continuation? In order to define this analytic continuation, if you focus back on the definition of how we define the projected correlator, so the delta function just defines that you are constraining the distances between all the n and minus 1 by 2 particles to be the maximum one, basically integrating out every other information. And the major emphasis is on the weights that you multiply. So what you can do is basically that you can write these weights as the sum of all the particles that are contained in your subset. So basically you take um, a random subset of your particles, right? And then in all these, in the subset, whatever is the number of particles, you sum their energy fractions raised to the power n and subtract out all the contributions of the subsets that you would have already considered. Now, by doing this recursive procedure, so by doing it recursively, what you can show, for example, for just simple two particle situation, this complicated function would actually simplify. Just if you have only two particles with energy weights Z1 and Z2, let's say. So for one particle correlations, you just simply get the sum of momenta of the particles. For two particle correlations, you can actually write it as the sum squared minus this, which is just some, if you simplify it's just the product of the energies of those particles. But anyways, the essential point here is what you realize is that these weights are always just simple polynomial functions of the energy fractions. And I know that polynomials are analytically continuable. Since I can continue analytically polynomials, I can really generalize this situation for any general value of n. Now, of course, for any general value of n, these weights are not going to be truncated to a specific sum, and you will in principle get an infinite series of these weights that you need to consider, which is basically thinking in terms of like literal correlating the particles. You can think of that now if your n is non-integer, you're literally correlating each particle in the jet with every other particle in the jet, looking at different subsets of these particle correlations. So although all of this is really interesting, but it's actually quite prohibitive, because even for a jet with, let's say, m being 30 particles, even if you had 30 particles in your jet, the amount of computation power that you require in order to do this recursive procedure is really prohibitive. You would require almost 2 to the power 60 units of computational time in order to compute this, which is almost impossible, really. So this was one of the biggest computational challenge, because of which many of the nice properties of these analytically continued projected correlators was never utilized. And at this point, I want to talk about something which we developed here at Nikhef. Like, we developed a completely new way to organize these energy correlators so that the computational challenge that we had so far is entirely removed, really, so that we can really try to start utilizing the promising properties of these analytically continued projected correlators as well with equal ease. Okay, so what's the idea behind our new approach? So first, just to repeat things, like the problems that we had with the original formulation is, first of all, it's really computationally impossible to compute it for this general family of analytic continued projected correlators. However, what is very relevant to realize is that this traditional approach really relies on all the n(n-1/2) pairs of distances between the particles. Now, even for a 4-point correlator, you realize that for 4-point correlator, in order to find which one is the maximum separation, you would have to compute 6 pairs of distances, 6 distances. However, if you look at just the geometry of these points, you realize that not all of these separations are actually redundant. You don't require to know the information about all of these distances in order to determine what is the largest distance, because only 2n-3 of them are actually like non-redundant distances that govern what is the full geometry of your 4-point. It's just a simple geometry problem at that point, right? So if you could find a set of parameters that allows you to remove this redundancy and allows you to make use of exactly this 2n minus 3 variables that are non-redundant. It already allows you to provide this computational speed up, and that's precisely what we do. So what we did was the following. Instead of asking about computing distances between all random pairs of particles, you fix a specific particle and say that, let me call this particle as my special particle. And I'm going to say that I'm going to compute distances with respect to only this special particle. All the particles in the jet are computed only with respect to this special particle. Now, in spirit, nothing is special. So you actually inclusively sum over all possible choices of your special particle in the jet. So you modify your definition of the correlator at two places. First, you modify the distance measure, because now the maximum separation no longer remains as the separation between the different particles, but with respect to this special particle. And you isolate this special particle, which you later sum inclusively over. Okay, so now already before doing anything further with this, I can already argue from simple triangle inequality that this modification of modifying my observable directly is already a good measure of the overall scale, because by triangle inequality, I know that my new measure R1 is related to the old measure RL, because it has to be between RL by 2 to RL. So provided that my distances that I'm talking about are large enough, I know that this is basically a relatively good measure of my overall scale of the problem. Why this allows you to have a computational speed up? That could be looked at by looking at the cumulative distribution. So if you look at the cumulative distribution, you can write down this entire thing that we have. Oops, this is not good. Sorry. You can write down this entire summation and reduce it to look at basically just, so what this bracket tells you is basically that you are looking at, so you have a special particle, and around the special particle, you create a disk of a specific radius r. Look at all the particle content inside this disk of radius r, sum the total energy density inside this disk, raise it to power whatever you like, which is actually quite simple, because now every different endpoint correlator basically reduces to just looking at the total energy density inside the disk raised to some arbitrary power, and that does not cost you any time. So which allows us to actually literally have a computational scaling going from 2 to the power 2m to order m square log m for any general n. Yeah, I'm happy to take at this point question about this approach before moving forward.
It seems like a very, very clear way of how this should be done with respect to the usual way. So was this sort of, had other people thought about other ways of improving the computational intensiveness that were different from this one, or was this really the first idea you guys came up with and then you were the first one?
So, okay, I can tell you like, so I did also like, prior to this approach, I did 2 more projects where we did try to do some kind of computational speed up without modifying anything about the original definition, but using a completely different idea that allows us to also have some amount of computational speed up, but not this drastic really. So since we were working on this direction of like trying to really make use of the full class of this family of energy correlators, the computational speed up so that it could be literally utilized on the available experimental data was very crucial for us. So I don't think the computational and emphasis was ever like dealt with so far. Like if you look at the original paper where this analytic continuation or some things were defined. It was already defined, I think, in 2020 paper. I think it's a 2020 paper. So 6 years back. So all of this is comparatively very recent, honestly, right? But 6 years back, when they defined all this definition and everything, they did realize that there is supposed to be a better algorithm in order to do these things. And in their paper, literally, they could do it for 4 particles because of this limitation, really. But beyond that, they did not try anything like any other way of trying to organize or making it better, really.
Okay, thanks.
Yeah. Okay. So I told you that, okay, things, I mean, even if you reorganize things the way I proposed, it works very good. But let me also give you a clear visualization that whatever I claim is actually indeed what we see as well. So here in this plot, you can see I'm comparing the results for different n values with the old way of doing things versus the new way I defined. So you can see that in the perturbative region, the differences are actually really, really small between the old and the new way of doing things. And the only visible differences are actually in the transition region, which is why I earlier said that, okay, transition region is the one which is not the best understood regime, really. And in the far deep non-perturbative region, you see that, okay, again, things agree very well. All right, so I don't want to go with the more technical details about the new approach, but let's see what are the better things that we can now do with this new approach. So of course, we can compute any values of n, whatever n-point correlator you would like. And this plot really compares the computational timing that you would require in order to compute things with our new approach versus the old standard way of doing things. And you see that already, like for 5-point correlations projected, the old approach takes roughly of the order of 2 hours in order to compute things, while all the other n values are completely unachievable in the old way of doing things, really. And for us, it all just takes like 18 seconds. And maybe I should mention that this is all done really on a single core on my laptop, really. So it's that fast. Okay, good. So what? That I can compute all values of n, fine. But what we really could do was, so with this approach that we now had, we took the available CMS open data for PP collisions and we tried to, for different values of n, we tried to literally fit this power law behavior and compare this extracted power law behavior from the CMS open data against our theoretical expectations. So red is really the CMS open data that we extract the power law coefficient for. And what you see is that for large values of n greater than 1, the power law behavior actually lies between these two blue curves, which correspond to your DGLAP eigenvalue solutions of the DGLAP anomalous dimensions. And you see two curves right now because we plotted separately for the solution for the quark and for the gluon separately. While in principle, there is some mixture of quark versus gluon in the final jet mixtures that you observe. So the ultimate curve has to be something in between. But we do see that, okay, the extracted experimental result lies well between our theoretical expectations, which is nice. However, when n is less than 1, you see that the experimental result really saturates to a value, while your DGLAP solution, even if you would have taken any mixture of quark versus gluon, actually the gluon solution diverges. So no combination of quark versus gluon fractions would be able to explain the saturation that you observe in the experimental data through DGLAP. However, this is not really unknown in the field. People know that when n goes to 0 or n goes close to 0, you actually gain more sensitivity to also the soft physics in the problem, and it's no longer just collinear physics, and you start seeing that sorry, the experimental extraction starts looking very close to what's the BF-Gill anomalous dimension in this regime. So this was a very nice result that we could obtain using the available CMS data by utilizing our approach in order to do any point energy correlators. Okay, but now I want to also now talk about energy correlators in the presence of heavy ion collisions in medium. So in the presence of a medium, like because of the presence of the quark gluon plasma, you introduce new scales in the problem. For example, you introduce like the Debye screening mass, the path length, the medium temperature, the coherence, decoherence angle, you name it. So many new scale come into the problem. So it's no longer just the simple physics that you saw in the case of PP collisions. And the hope is that the presence of these scales are going to be somehow imprinted in the correlator distribution as a modification of the PP baseline that we want to observe. And in fact, like you hope that in the perturbative region where we have more control of things, you would also see some kind of modification of the power law scaling in comparison to PP. And several attempts have been made actually theoretically in order to understand this. So you see, like if I plot just the angular scale between the angular distance between the particles, you see at small enough angular scales, things look more like exactly how the vacuum baseline. So nothing changes. It keeps looking at like a vacuum jet emission actually. And at some point, which is set by the scales of the medium, you start seeing that there is a medium-induced enhancement of the correlator. This was a very first paper, and then like many other works were included. So this particular paper then starts showing that, okay, this large enhancement that you see at a specific angular scale is just a too much oversimplification of the problem. Since we do not know the complete full matrix elements, if you had the information of the full matrix elements, you would not see a very large enhancement like the blue or the red, but realistically, you will see some amount of enhancement still in the large angular region. And then later, some works also like try to deal the problem with a factorized approach where they are able to actually talk about the resummation of new kind of logarithms that appear in the presence of medium and how they can resum it in their framework. Okay. Other than theory developments, it's also really exciting that experimentalists also measure that quantity of interest. And recently, there had been measurement of these energy correlators by the CMS collaboration. So on the left, you see so they did it for the simple 2-point energy correlator, just correlating 2 points in the jet, not so far about how the higher point correlators would look like. But you start seeing, if you take the ratio between lead and PP, you see modifications at different regions of this plot, right? You see some enhancement in the small angular regions, you see some kind of a dip in the intermediate region, and then you see there is a large angle enhancement. And I don't know which way to say it, but of course, fortunately or unfortunately enough, many different approaches actually end up explaining different regions of the correlator distribution. So there is still a lot of work to be done in order to properly understand the theoretical, the experimental data that we have for energy correlators, to understand the different regimes. However, much of the consensus in the community is basically driven by the fact that in the large enhancement seen in the tail of this large angular distribution, large angular region of the distribution, emerges basically because of the presence of both the medium induced radiation as well as the presence of medium response. Now, many of the things are actually sort of still better understood about the 2-point energy correlator, but you can also ask the question that in this scenario, would going to higher point correlators really help? Do they add any kind of more information that I could not find through the use of just the standard 2-point correlator? or the 2-point correlator is literally enough to tell us about everything there is to know about the different medium. Yeah. Okay. So now I come back to the actual title of the talk. So I want to talk about like higher point correlators and using jets in order to study these higher point correlators in the medium and try to understand whether they do add any kind of information, really non-trivial information. Okay, so the way I would like to do it is basically use a similar factorized approach as you do for the projected correlators in the vacuum basically. And in the presence of the medium, I would claim then that the same kind of factorization formula would hold, with the difference that now your J, the jet function in the medium, gets modified. And this jet function, the way it modifies, is calculable at different order expansion in the number of medium vertex insertions. So if I insert no medium interactions, then it's just like vacuum, which is the first component of my jet function. At minimum, you have to introduce two insertions from the medium, and that's the first non-trivial medium-induced or medium-modified jet function that you would obtain. And similarly, you can keep on introducing more and more number of medium vertices in order to compute things. You can ask the question why there is no JQ1, why you cannot have a single insertion. It's simply because since you always do a mod square of things, those kind of contributions just become zero in this setup. So you literally require, at least in order to have like two insertions in order to be able to actually get a non-zero contribution. Now, this approach has been currently like being developed. It's not a fully developed framework still, but this work has been, is an ongoing work with people or like Varun Vaidya and my collaborator Balbir Singh. So we used this approach of doing skate-based factorization in order to like compute the general endpoint correlators in the medium. And then what you can write down in this approach basically is that the jet function is written down in terms of two components. The first component corresponds to the true medium in modified computable part. This is perturbatively computable, and just at the leading order, like at one loop order, it becomes similar to what you have already seen in other frameworks like the GLV framework developed by Vitev. And the second component is basically a non-perturbative component, which describes your medium function and is governed by your medium correlators. But the nice thing about this approach, this setup, is basically that this medium function then can be written down in terms of just the matrix elements of some operators described by the medium. And in principle, this is some object you could compute on the lattice, since it's a non-perturbative quantity. So the hope with this whole scenario is then that by taking inputs from the lattice and perturbative computations, you can in principle have a complete model-free computation of jet-based quantities in the medium. Now, if you use this framework in order to compute the endpoint correlators, so basically, the full result is non-trivial. So you could simplify things by taking two simple limits. So the first limiting scenario that we looked at was when the formation time of the emission in the medium is much smaller than the length of the medium. So in that situation, you see like the jet function for the endpoint correlator simplifies to this form. So you see that the correlator is actually like enhanced by the length of the medium. It goes non-trivially with the angular scale chi, but at n equal to 0, it saturates to a finite value. It does not ever diverge. And similarly, if your the formation time of the emission that you had is much larger than the formation the length of the medium, then it's basically you see that a new different kind of logarithmic structure emerges in the presence of the medium. So, which is really nice to see because most of your models will not be able to show you such kind of like formation of this new logarithms. And of course, the full numerical result is much more harder to read. This is just an interpretation that you can do by taking these simple limiting situations. However, the key points to note here are first that in either of the two situations, even if you take n equal to 0, nothing diverges, which is very different from what happens in the presence of the vacuum. Because in the presence of the vacuum, So in the case of vacuum, basically like your angular, depending on your angular scale, actually, okay, maybe I should say it differently probably, because in the vacuum, for any kind of endpoint correlator, you just get, at fixed order, you just get a 1 over angular scale enhancement. And all the n dependence, a non-trivial n dependence comes from the resummation through the anomalous dimensions. However, if you compare this 1 by chi scaling in the vacuum with the scaling that you observe in the medium, you see a complete modification of the power law already in the medium, which goes much more non-trivially, like even a logarithmic in certain regions of the phase space. Okay. So we used our analytic computation in order to compute different endpoint correlators taken ratio with the standard 2-point correlator. And you see basically like, so basically like for higher point correlators, you see you gain almost negligible when you take the ratio with the 2-point correlator. However, if you look at the small n correlators, you see that you start getting more amount of information about medium induced effects compared to the standard 2-point correlator, which is nice. So basically you now our study concludes basically that you gain mild amount of information by utilizing more and more and more points in the to do the correlations. But if you do actually go to this small n correlators, that can improve your identification of medium induced effects and enhance the amount of medium induced effects in the final correlator distribution. And similar results were also seen from doing the Joule simulations, but in order to have a fair comparison with our analytic computations, which were done in the single scattering limit, we turned off like heteronization effects, medium response, medium evolution, and of course, also the initial state radiation effects as well. But quantitatively, they look very similar with our analytic computation. And basically, this is what I said already from the previous figure. So you can again look at you can take the region of the power law, you can fit it to a power law scaling. And if you plot this power law scaling for different values of, okay, I use here nu in our paper, but this is exactly like n. So if you look at this power law scaling for different values of n, you see that for higher point correlators, and this is for the 2-point correlator, so the ratio would have been 1. So there is some amount of information that you gain by looking at the higher point correlators. But by looking at the small new correlators or small n correlators, you literally actually gain completely non-trivial amount of angular information that is not captured in your 2-point correlator. Okay. So before I move to the final part of things, is there any questions?
Yeah, sorry. Maybe 2 slides back?
Yes.
Or slide 7.
This one?
Yeah, I'm just trying to understand. So when you talk about these limiting scenarios,
Yeah.
am I thinking these as physically this jet is now forming outside of the medium in the second case? And
yeah. So right now, this is just a single scattering limit. So there is only one scattering, one emission, right?
okay.
Right? And then you are talking about the formation time of this emission.
Okay.
Whether this emission was formed inside the medium or outside, basically.
Okay.
It's a late time emission or an early time emission, for example, right? Yeah.
Okay, thank you.
Yeah, yeah. Right. So Yeah, please.
Or did you
Please
want to
go ahead.
continue on this?
Yeah.
Oh, so I had a different question about the small x physics. So what kinds of new physics can you learn by gaining access with your energy correlators to small x physics? What kinds of observables can you say new things about?
It's again a very good question. I will go back here, let's say. So there are these small pictures that I have here, for example. This literally is trying to answer what you are saying. So if you look at like the small x region, you're actually accessing a completely different regime of your phase space, like physics actually. So let's first go away from small x. If you look at the traditional large N correlators, then it's just simply like a DIS kind of scattering, right? So you have this, let's say, proton, and then you have a particle coming in, you have a DIS kind of process that you are looking at. When you go to this small n, actually, what you are really probing, so the way the gluon emissions are actually happening with this, because now your energies of these particles is really, really soft, right? So it cannot scatter things. What it can do is like just this virtual exchanges, it can still do. And this is very close to what you do in terms of the forward physics processes. So you're looking at basically the forward physics versus more like central physics regimes when you're doing at large N. So you're really probing a completely different phase space of the the kind of gluon exchanges that are happening with the proton or nucleon, for example, in this situation.
Okay, thanks.
Uh-huh. Yeah. Yeah, but my takeaway point here is essentially that indeed, like at least in the single scattering scenario that we assumed, or the calculations we had, we see that basically you gain in terms of the angular information that is contained in an energy correlator. You find that more or less similar energy angular information is contained in the higher point correlator. Of course, it's enhanced because if it was not, then the ratio would have been 1. So this ratio is still larger for the 3-point, for example, but completely more like non-trivial information in terms of the angular scale is contained in a correlator which you are looking at as a non-integer small n correlator, really. And similar things we also see basically in the Joule simulations at this point. And this is right now with a plot with all the other effects added in. So basically trying to say that even if you include other effects like hadronization effects or medium response, it does not change the fact that we see in the simple situation that we had in our analytic setup. Yeah. Okay, so now in the very final part, I just want to quickly tell you about, like, so far we said that we do see that, okay, small n correlators seem to be like relevant for being able to actually see clear signatures of medium induced like modifications or medium induced signatures in contrast to PP. I want to have a more like statistical notion of how well can I discriminate between lead and PP distributions. And I want to ask like to what extent really this small n or in general PENCs allow me to have the ability to probe this medium induced dynamics in contrast to the vacuum baseline. And now, standard jet substructure observables, take for example, jet multiplicity or jet mass, whichever you like. The nice feature about these standard jet observables is basically you take a jet, you compute, let's say, jet mass, you get one value out of it. That's it. And for that, many tools exist. For example, doing this ROC curves in order to assess what is the discrimination ability. However, for energy correlators, you take a jet, you compute energy correlator, out comes a full histogram, right? So which means they are intrinsically different from our standard jet substructure observables, and you need to carefully treat the subtlety of the intra-event statistical correlations. So that means you need new statistical tools if you want to statistically gauge what is the amount of discrimination power that you gain by using this higher point correlators. And very quickly, because I guess I'm running out of time as well. So very quickly, like a simple thing which a measure which was used other than the ROC for standard jet observables is something what is called as delta discriminator. You can basically, I'm really sorry, I'm missing a square, I'm missing a bracket around the square. So it's the difference between the two jet probability distributions squared. So basically looking at the size of fluctuations in the two samples divided by their total mean. This is really similar to, in some sense, the chi-square statistics, basically. Just a bit different way of formulating the chi-square statistic. So if your delta is close to 0, it implies that you don't gain any discrimination between your sample A and sample B. If delta is close to 1, you get a perfect discrimination between the two samples. And what lambda is, lambda could be any kind of classifier that you use. In case of jet, then it can be any kind of jet substructure observable, for example, multiplicity itself. So people have defined and used this delta measure in order to perform something like, for example, quark versus gluon jet discrimination, using different event generators in order to do so. And basically, they find that this delta discrimination actually not only allows them to look at the discrimination between quark versus gluon, but also gives them some statistical measure of the discrimination ability between the different event generators as well. But in order to like apply it, all these statistical procedures for heavy ion or energy correlators, it's not really about question about heavy ion. It's a question more about like doing it for energy correlators where you do not have just a single value per jet. You need to do you need to take care of the correlations between the different particles at different. So a single event contributes to basically multiple bins in your histogram, and you need to take into account these correlations. And in order to do so, we modified this triangular divergence by including these correlations. And I'm just gonna ignore this right now and go show you the final plot. So this is the plot we generated from utilizing this new delta measure for using simulations from Joule. And what you really see is basically, so here lives your delta for your 2-point correlator. So basically you see that, okay, if you keep on adding more and more number of higher point correlators, you are not going to gauge much more discrimination ability using this statistical measure of delta. But truly, like this large discrimination ability comes from including or going to smaller n correlators that we also saw in our theoretical construction, actually. And this, of course, comes only after you include the notion of medium response in Joule. So which is why only the red curve, which contains recoil, shows this enhancement, while the situation without including this medium response does not show this is basically enhancement. So it's suggesting that it's really this medium induced response that's generating this larger ability of discrimination that we saw theoretically in our simple considerations. Okay, so with that, I would like to end. I'll just present a very, very brief summary. I tried to tell you about energy correlators, why they are interesting theoretical observables. And then I introduced a new way of doing energy correlators that introduces a parametrization that's really fast, allowing us to utilize the full potential of these observables. And there is a lot of things to look forward to, which I did not introduce in this talk at all. You can generalize it to studying more differential correlator distributions. We also have like some results where we are trying to investigate the like back-to-back region of the correlators, higher point correlators using our approach. And we also are trying to understand non-perturbative effects for general values of endpoint correlators better through our parametrization, really. Thank you for your attention.
So are there any questions currently in the room still? I guess not. So I do have one more question, which I was thinking about. So you have this region of n where you go below one, but what about like if you go above one? I would say you treat n as an integer, but is there also higher integer steps where you can also go to decimal, like have for say 3.1 as your n, and would that then be a 3-point correlator with some small physics effects, or what
No,
would it?
no, good. So you can talk about any non-integer value for n greater than 1 as well, right? But I would say you think literally about, let me just go back a bit. So the way you literally think about any of this is basically you think about like now you have this, think of it as a binomial expansion, just simply a binomial expansion, right? And let's say if you have a non-integer power to this binomial expansion. So what is the meaning of this non-integer value? It's literally setting what is the amount of weight you give to different particular combinations of the terms in your expansion. So then what 3.1 would mean, so in general, your coefficient would have been 3. Now it will be modified with a 3.1 raised to a non-integer power as well, right? Because if it would have been a standard 3, you would have gotten like 3 times z1 square. Now you would get 3.1 times z1 to the power, let's say 2.1, something like that.
Okay, and what kinds of different, like what? I get that it's a different expansion, but what kinds of different information does it lead to? Like, is it just a different way of scaling the different variables or contributions?
So you think about it as that you are weighing things differently, right?
Yeah, okay, yeah, I guess so. Okay.
Yeah. So also you can think about like in simple terms, like as I said, like if you focus on this equation, you literally see that what you have splitting functions, and your definition of your anomalous dimension is you are taking n moments of the splitting functions, right? And then let's say if you are talking about n equal to 2, you are looking at a specific moment of the splitting function. Let's say it's governed, so it's x squared times p of x, which is basically so if it was 1, then it's xpx, which is just the mean. When you take x square, you're looking at the variance. If you raise it to higher and higher powers, you're basically looking at different modifications of your splitting functions. Like you're taking your splitting functions, weighing it differently, and looking at the different moments of it, right? So you have a clear notion of these things as mean, variance, or let's say skewness, or whatever higher moments in terms of integer. But of course, you can also do non-integer, right?
Okay. Okay, thanks.
Yeah.
So if there aren't any questions online as well, which I guess not, then I would thank our speaker once more.
Mhm.
And then stop the recording.